everybody, and welcome back to another Gregorius Maths Prerequisites video. Today I'm going to be introducing calculus. Namely, we'll be looking at the notion of what a limit is. This is a very, very important idea in calculus, and it's what most of calculus is based upon. Derivatives, integrals, those two things, those main things in calculus, are both based on limits. So I will introduce limits today. I'll introduce the definition, the intuition. Then I'll introduce derivatives, and then we'll move back to limits because learning how to evaluate derivatives is very helpful in evaluating limits. Okay? So, say we're given some function f of x. So what this notation means, if say for example f of x equals, I don't know, x squared plus 2x minus 1, for example. Okay, what this is equivalent saying y equals x squared plus 2x minus 1, and that's going to be some kind of parabola. Alright, it's spoiler alert, it won't look anything like this, but some parabola, like, you know, that type of shape. Of course it won't be, it'll be shifted along somewhere, maybe down. It will have roots. However, that's roughly what it will look like, okay? So, here's the notation for a limit, okay? We say a limit as some x goes to a, okay? So, a is just a number. It can be infinity even, which is technically not a number, but like, this is calculus what does. It introduces the notion of infinity, kind of. So this a can be pi, it can be e, it can be infinity, it can be negative, it can be 0, whatever, okay? Of f of x being equal to L, okay? So what this is saying is, say we have our f of x, which looks like this, okay? So we have some point L here. That's L, okay? Now we have our our A here, right? Okay, so the idea of the limit is, as x gets sufficiently close to A from the right-hand side and the left-hand side, okay, our f of x should get sufficiently close to L. Okay? So, say we have our f of x here. Here. We have it here as well. Well, we have it like this, we have it like this. We can clearly see that somehow this, as x get closer to A, this f of x, this output, gets closer to L. Okay, so how do we make this rigorous? So first of all, let's write in English what we're saying. As x gets closer to A, okay, f of x gets closer to L. Okay? Now, let's define this closeness as just being some epsilon greater than 0. Okay? Now, epsilon, don't be intimidated, epsilon is just a Greek letter, and it's usually used for denoting small numbers. Okay? So this getting closer to A it's not on top of A, x is not equal to A, so the distance must be greater than 0. Okay, it can be very, very small, it can be 0.001, etc., etc., but it's bigger than 0. Okay? F of x gets sufficiently closer to L. Okay? So, for the sake of the definition, this right here is normally referred to as delta, and this right here is normally referred to as epsilon. Okay? But they're both Greek letters, and if you hear and they're used in what's called epsilon delta definitions. So they're used for making limits like this rigorous. They're used for making continuity rigorous, etc., etc. Basically, small numbers greater than 0. Okay. So I'm about to use some very, very mathematical notation here. So, for all epsilon greater than 0. So this means given any epsilon I choose, okay? So, say we have our graph again, f of x. Okay? L is here. Okay, we have some epsilon greater than 0, L plus epsilon. We have some L here, L minus epsilon. We have our A, okay? We have our A minus delta here. We have our A plus delta here, okay? And they're mapping onto like this, okay? So it's the idea of this range getting closer to A, and this range getting closer to L, basically. So as we squeeze the x-axis closer to A, the y-axis gets closer to L, if the limit exists, okay? So for all epsilon greater than 0, there is some delta greater than 0, okay? So this corresponds to this delta here being greater than 0, such that, okay, this is just shorthand for such that, 0 is less than this range here, okay? So 0 is less than the distance between delta and A, okay? Sorry, is less than the distance between such that 0 is less than the distance between x and A, okay? Is less than delta, so that guarantees that x minus A is within this range of radius delta, okay? And that implies that the distance between L and f of x is less than epsilon. So, what we've written here is the definition. So let's decipher this one more time. Given some epsilon greater than 0, so this corresponds to the squeezing of the y-axis, getting closer to L. There is some delta greater than 0, so this first part here corresponds to the distance between x and A being greater than 0, okay? And epsilon being greater than 0. So as we get closer, as we squeeze the y-axis, the x-axis squeezes too, okay? Now this part here, this guarantees that this guarantees that the distance between x and A is less than delta. But this part here guarantees that x is not equal to A. So there is still some distance, and it's within this range, okay, of A plus delta and A minus delta. We can choose delta 0.00001, okay, and the distance will be smaller than that delta, okay? And this therefore implies that as we squeeze the x-axis closer, this part says that the y-axis squeezes closer to L, okay? Because the distance between L and f of x is getting closer. So the distance between L and the y-axis is less than epsilon, which is pretty much saying, this part here is pretty much the y-axis version of this part here, okay? And that's my introduction to limits. See you in the next video.